This video is a slightly modified version of a talk I gave for the Greater Boston chapter of the ACM about a dice problem that blew my mind. The problem statement goes like this. When you roll two standard six-sided dice and add them together, there's a probability distribution on the sum that you get. For example, the most probable sum is 7, and the probability of getting snake eyes is 1 in 36. Does there exist another, non-standard way to label the faces of the two dice with positive integers that gives the same distribution on the sum? The two dice don't have to be labeled the same way, and a die is allowed to have multiple faces with the same label. A very sensible way to go about solving this problem would be to first narrow down the search as much as possible by reasoning about it on pen and paper, and then, if you're comfortable with computer programming, write a program that exhaustively searches the smaller space. The solution I'm about to show you is not that. It's a kind of miraculous pen and paper only solution that a friend showed me some years ago. It goes like this. Start by supposing you have a die with custom labels and consider this polynomial, where the coefficient of x to the k is the number of faces that have label k. For example, for a standard die, it would be x plus x squared plus x cubed plus x to the fourth plus x to the fifth plus x to the sixth, where all the coefficients are 1. For a non-standard example, here's a die that has a 5 on two of the faces and 9s on the rest of the faces. Its polynomial is 2x to the fifth plus 4x to the ninth. Okay, so why are we looking at these polynomials? Believe it or not, the dice problem becomes simpler when we view it this way because, it turns out, taking the probability distribution on the sum of two dice corresponds to just multiplying the polynomials together. By way of a concrete example, let's ask, how many ways are there to get a 7 as the sum of two standard dice? Choosing outcomes for the two dice that add up to 7 is the same thing as choosing a term from the first polynomial and a term from the second polynomial whose exponents add up to 7. And the number of ways to do that is the coefficient of x to the 7th in the product. Similarly, we can imagine rolling two of the non-standard dice I showed earlier, and this corresponds to multiplying the weird polynomial by itself. In this case, it's not possible to get a 7 as the sum, and by the same token, the coefficient of x to the 7th in the product is 0. But it is possible to get a 14. In fact, it's very possible. There are 8 ways to choose one of the 5s from the first die and one of the 9s from the second die, and an additional 8 ways to choose one of the 9s from the first die and one of the 5s from the second die. So in total, there are 16 ways for the dice to have a combined value of 14. As a last example, we can roll one standard die and one weird die. Again, tallying up the number of ways to get each possible total is the same thing as distributing out the product and collecting like terms. The annotations here show the number of ways to get a combined value of 11, which is the coefficient of x to the 11 in the product. Finding non-standard dice that give the same distribution on their sum now corresponds to finding two different polynomials that have the same product as the standard one shown here. The one-sentence summary of the rest of the talk is that this equivalence we just established, combined with the fact that polynomials over the integers have unique factorization, means that we no longer have to do a big search on a computer. We only have to hand-check a few possibilities. All we're doing now is fleshing out that argument and throwing in a few more tricks and pictures. Here's one detail we have to fill in. We're trying to replace a question about dice labels with a question about polynomials, so we need to show their equivalent. We saw how to turn a die into a polynomial, but we still need to know how to reverse the process and turn a polynomial into a die. On the face of it, it's straightforward how to convert a polynomial to a die. We just say, for each k, there are ak faces having label k. This does reverse the process when it works, but the reality is that not every polynomial can be turned into a die. They have to satisfy certain constraints to be valid dice polynomials. One of those constraints, which may seem pedantic to even mention, is that the coefficients ak have to be non-negative integers. There can't be a negative coefficient because, for example, there can't be a negative number of faces that have label 3. The second constraint is that the labels on the faces have to be positive, so 0 is not a valid label. What this translates to for the polynomial is that a0 has to be 0. The third constraint is that the die has 6 faces, so the sum of all the coefficients has to be 6. Notice that we can rewrite the second and third constraints in terms of the values the polynomial takes at specific settings of x. The second constraint says that evaluating the polynomial at x equals 0 gives 0, and the third constraint says that evaluating the polynomial at x equals 1 gives 6. These versions of the second and third constraints will come in handy later. Now we have the full picture of the equivalence between dice labels and polynomials. We can always convert a die to a polynomial, and we can convert a polynomial to a die if and only if the polynomial meets the three constraints. So now we really can replace the search for dice with a search for polynomials. We're looking for two different polynomials, say b and c, whose product is the same as the one for standard dice, shown here. But again, we don't need to do a big search. All we need to do is decompose everything into irreducible factors. The polynomial for a standard die factorizes as x times 1 plus x times 1 minus x plus x squared times 1 plus x squared. So, substituting that, here's the pile of irreducible factors that need to be allotted to b and c in some way. I'm going to represent b and c as baskets, each of which can hold some of the factors. And bear in mind that at the end of the day, the product of what we put in each basket has to satisfy the three constraints we established before. Let's first look at the constraint that each polynomial has to evaluate to 0 when x equals 0. Only two of the irreducible factors do that, namely the two x's, so each basket has to get one x. Next, we have the constraint that each polynomial evaluates to 6 when x equals 1. If we substitute x equals 1 into each irreducible factor, we get the values annotated on top here. To get a product of 6, each basket has to contain one of the factors annotated with a 2 and one of the factors annotated with a 3. That leaves us with just the two factors of 1 minus x plus x squared to divvy up. If we put one in each basket, then the contents of the baskets are the same, and we get the standard dice polynomials. So let's try putting both factors into the same basket and see what we get. After expanding all the products, we end up with these polynomials: x plus 2x squared plus 2x cubed plus x to the fourth, and x plus x cubed plus x to the fourth plus x to the fifth plus x to the sixth plus x to the eighth. These polynomials work. We did get lucky here. We didn't do anything special to make sure b and c satisfy the constraint of having non-negative coefficients, but they do. I'm not aware of any deep reason this had to be the case. As far as I know, that's a coincidence. And the fruits of that coincidence are this pair of non-standard dice, whose sum has the same distribution as the sum of two standard dice. These are called the Sickermann dice, named after George Sickermann, who invented them in 1978. What blows my mind about this pen and paper solution that my friend showed me after the interview is not so much that it finds an alternate set of labels, but that it proves that that's the only alternate set of labels, and the heavy lifting in the proof is done by unique factorization of polynomials. As far as I can tell, this solution isn't just dressing up a different solution in fancy algebraic machinery. The use of polynomials really is essential. And it's very not obvious to me, upon looking at the original question about dice, that polynomials would be relevant. So that's the dice problem whose solution blew my mind. Thank you.